topic for today's discussion is variation of acceleration due to gravity due to rotation of the Earth. But first we need to know that due to the peculiar shape of the Earth is not a perfect sphere, it is an object spheroid. It means that at the poles it is flattened and at the equator it is bulged. Okay. And the value of G since the value of G on the Earth's surface varies inversely as the square of the radius. We have done it earlier also, G proportional to 1 by R square. So the radius at the equator is more than the radius at the poles. So the value at the poles is more than the equator. The value of G at the poles is more than the value of G at the equator. So the weight of a body at the poles is more than the weight of a body at the equator. And this equation is given as, let me write the equation, the value of G dashed due to the object spheroid shape of the Earth, G dashed is equal to 978 1 plus 0.00531 sine square lambda centimeter per second square. Centimeter per second square. Now this lambda is the altitude of a place. This lambda is the altitude of a place. At equator, this lambda is equal to 0. So sine square lambda is 0. So G dashed is nothing but 978, which is its value. And if you increase the value, for example, lambda is equal to 90 degree there at the poles, then you have sine square lambda is 1, and you have value of G dashed is equal to 978 1 plus 0.00531 into 978, and you will certainly get a value which is more than the value at the equator. Okay. Now, due to the rotation of the Earth, what happens due to the rotation of the Earth? Due to the rotation of the Earth, what happens is that there is a centrifugal force acting on the body. There is a centrifugal force acting on the body which tries to make the body fly off from the surface of the Earth, right? Which tends, which makes a body fly off from the surface of the Earth. And this force is maximum at the equator and smallest at the poles, because the radius at the equator is more than the poles. Now, since and this force acts in a direction opposite to the force of gravity, and this centrifugal force acts in a direction opposite to the force of gravity. So the actual weight of the body appears less than its true value. So the actual weight of a body appears less than its true value. Let us prove it. So take a body, suppose this is a body placed at an altitude or at a latitude of lambda. This body is placed at a latitude lambda, okay, on the surface of the Earth. Now, the angular velocity of rotation of the Earth is given as omega, means the Earth is rotating like this, omega, with the angular velocity omega, not W, but it is known as omega. Okay. Now, the body describes a circle of radius. This is the body. It will describe a circle of radius, this one, right? This is the circle which it will describe. I am redrawing the circle. Yes, this is the circle which this blue circle is the circle which the body describes due to the rotation of the Earth. Now, radius of this circle is small r. Radius of the circle is small r, and the radius of the Earth is taken as capital R. So, since it is at a latitude of lambda, from this diagram you can see if this angle is lambda, then this angle is also lambda due because of alternate angles, and this small and this line is capital R, which is the radius of the Earth, and this is small r. from the geometry, we can write that small r is equal to capital R cos lambda, capital R cos lambda. So now the centrifugal force acting on the body along this direction is m omega square small r, m omega square small r, and the centrifugal force acting along this direction is m omega square capital R. Now, since we are wanting to take the weight of the body, since the body is placed here, it will be the force of gravity acts in this direction. Force of gravity acts in this direction. So, the component of centrifugal force which acts opposite to this force of gravity is this one, m omega square r cos lambda. Why cos lambda? Since this lambda, this angle and this angle, they are corresponding angles. So this angle is also lambda. And if we resolve this m omega square r into two rectangular components, then the component opposite to the force of gravity is m omega square r cos lambda. Okay, m omega square cos lambda. So finally, we can write that the weight of the body mg dash, or the net force with which the center of the earth pulls the body towards itself, mg dash is equal to mg, the actual weight of the body, minus m omega square. This here, this one is mg, right? This force is mg. So mg minus m omega square small r cos lambda, right? M omega square cos lambda. But since this r is variable, let us convert into capital R, which is constant for earth. Mg minus m omega square, instead of small r we can write r capital R cos lambda. So the equation becomes capital R cos square lambda. So mg dash is this. So what is g dash? G dash now becomes g minus omega square r cos square lambda, or g dash is equal to g, take it as common, 1 minus omega square r by g cos square lambda. So what happens at the equator? At the equator, lambda is equal to, at the equator lambda is equal to 0. At equator, lambda is equal to 0. So cos square lambda is 1. So g dash is g 1 minus omega square r by g. And at poles, lambda is equal to 90 degree. Lambda is equal to 90 degree. So if lambda is equal to 90 degree cos square lambda, it becomes 0 and g dash becomes equals to g. Now, as if this portion of the equation is in existence, then what happens is that this value of g gets lowered, that g dash becomes less than g. But at lambda equals to 90 degree, this becomes 0, so g dash is equal to g. So at the surface of the earth, you will get the maximum value of acceleration due to gravity is at the poles, and the minimum is at the equator. Okay.